Okay, good morning, everyone. Welcome to our session about optimizing LLM performance with caching. My name is Uri. With me is Sherin. We're both specialists from AWS. Sherin is an analytics specialist. I'm an AI specialist. And today we'll speak about caching LLM applications, basically. We took the agenda a top to bottom sort of approach. I'll give a brief intro about the motivation. Why do we want caching? Some caching design patterns. How do we architect caching solutions for LLMs? And some implementation notes. And then when we're going to deep dive into the OpenSearch implementation, I'm going to hand it over to Sherin. So to get started about the intro and the terminology, our story really begins after the successful POC, or once we went already into production, about what are the main challenges that we see customers are having once their application is already on the air. And the first challenge that we see is cost-related. You can see here a sample example of a typical e-commerce application that has about 100,000 product queries a day. In this example, I'm using a Claude 3.5 model, which is not even the most expensive or cutting-edge one. And even with this sample application, we see that the daily cost is about $750, which represents $22,000 a month. The second challenge that we see is often related to latency or performance. I know that this is an OpenSearch crowd, and we often look at performance in milliseconds. But for LLM, it's often in the seconds itself to get the response there, and that has implication. Two sample real-world examples where we saw this. The first was with a healthcare company application. They were having a summarization application using LLMs. And when we were testing the application before going on air, the latency was around 4 seconds to get the reply from the LLM, which was OK. It was something that the application could withstand. But we didn't take into account peak hours. So once we peaked during users' invocations, that really led us to significant latency problem. Also, in the healthcare area, compliance and regulation was also a concern, because this application included multiple invocations to the LLM. It wasn't just one single invocation. That company also wanted to minimize their LLM invocations and usage. The second example, again, it's an e-commerce company. Over there, their monthly cost was around $120,000 only for that LLM part, that only AI part of the application. And again, they were facing increasing latency issues, which was representing in customer satisfaction scores that were dropping there. So this gave us the motivation to see if we can reduce both the cost and latency using caching. At a high level, some basic terminology about caching. Caching is really where we have a short-term data store, where we store either some remote resources from a service or some remote computation. And then whenever we have some client request for it, we check to see if that request already happened in the cache. If it did happen, we refer to that as a cache hit. And then the response is going to be very, very fast and with hardly any cost associated with it. If the request happens and we didn't have it in the cache, then we have to invoke that remote service. In our case, it's an LLM, and then retrieve it. And then obviously, we have a cost attached to it and additional latency. So with that, wrapping up the introduction, let's talk about some high-level solution, or how do we architect a caching solution. And the most simple and straightforward implementation is a single-layer caching solution. In this case, the users input their query. We check against the caching store to see if we have that already in place, and we'll deep dive into that implementation in a minute. If we have that query already in the cache store, we respond to the users, and then no LLM invocation happened. If not, then we have to invoke the LLM there, and we need to store or cache the response that we're getting before returning it to the users. Another solution that we have is a multi-layer caching. In this case, we have 2 layers of caching. Here we would check first against the first layer. This could be, for example, a very simple implementation, or you can have your own business logic rules if you want to check against other caching stores there. But the same flow happens here. In case we have a cache hit, we return that to the users. If not, we then invoke the LLM and cache the results and send it back. When it comes to RAG, retrieval augmented applications, there are really 2 patterns that we see. One is a pre-retrieval caching. In this case, when the user inputs their request, we check it against the cache layer. In case that we have that found, we respond with the result. If not, then we go and invoke the knowledge base to see if we can find the relevant result, and then invoke the LLM for the additional downstream task. One of the main drawbacks of this sort of implementation is that in case our knowledge base is changing, that cache store might respond with some obsolete data. That's why we also have the post-retrieval caching design pattern, where we first do the retrieval, and then we check to see if that retrieval already was cached, and then we return it to the users if we did see it before. Otherwise, again, we're invoking the LLM and then returning the response back to the users. So up until now, I discussed where do we implement caching. Now let's talk about the actual implementation of caching. And the first decision that one has to make is, do we go with an exact key match or exact match versus semantic? Exact key match, just like the name implies, is really about checking whether the exact request happened before. And here you can see a sample example where I'm asking what is OpenAI, and in the first invocation, the response was within 3 seconds. And then when I'm asking it again, the response came back in 33 milliseconds. And again, there was no cost attached to it. The main drawback of this type of caching is that it's enough for somebody to introduce an extra space, and that's going to result in a cache hit. And then we would need to invoke the LLM again, and the response is again going to be, in this case, 5 seconds. So the pros of this approach is obviously it's very, very simple to implement, but it might not going to be very effective. Some recommended use cases for using exact key caching is if your application is really built around very short inputs like keywords, and then you have a good chance of having a cache hit. One of the other things that we saw is that if you have an architecture in place and you don't want to deep dive into the fine-tuning of semantic caching, this is a good implementation where you can have a placeholder as an exact caching. And then later down the line, once you see more patterns of usage, then you can implement a more advanced type of caching. And the third type is, again, if you have multi-layered caching, then you can use the first layer as an exact caching, which is very simple. And only in case we have a cache hit there, then you can go and implement a semantic caching as a second layer. With that, we'll move to the more advanced type of caching, which is semantic. By semantic, we mean we're going to cache the meaning of the request. And you can see here, for example, when I'm asking initially what is a cache eviction policy, I'm invoking the LLM, and the response is within 4 seconds. And this time, when I'm asking a similar question, but with different wording, what is cache eviction policy, then I still get a cache hit, and the response is within 1 second. There is a kind of a pitfall here when we're talking about semantic caching, and I would like to demo it quickly here. So if I'm asking an LLM, for example, give me a pitch. So obviously, the response that I got from the LLM is saying that, hey, I'm a language model. I can't give you any peaches. And then when I'm asking it, give me 2 peaches, since it's semantically very similar, I get a cache hit. And then, again, the response was instead of the original 5 seconds, I get it within 1 second. However, in the same setting that I have here, if I'm asking the LLM, tell me a joke, and it does tell me a joke, but then I'm asking it to tell me 2 jokes, it's still semantically very similar. And I get a cache hit, but this time I didn't get 2 jokes. So later on, we're going to talk about how do we fine-tune similarities. That's something that we need to take into account. So let's talk about the implementation or under the hood type. How can we implement, or the different approaches that we have for implementing caches? And the first option is really do it yourself, meaning not to use any of the ready-made frameworks. These are, I would say, the basic components of a caching layer. First, we have some custom business logic. Again, it's really up to you for your implementation to check against permissions, for example, any pre-processing that you want to have. Then there is the query vector store. This is where we're going to check for similarities. Obviously, the embedding model, where we're going to embed the request and check that against the query vector store, and a cache store, which is going to actually retrieve the results, and the eviction policy. How do we keep the data in our cache store fresh? Now, I want to highlight here that there is a kind of a paradox here. And the paradox is that while we're trying to reduce latency, introducing caching actually introduces latency. If you look, for example, in this example, let's think of a query for the first time in our system. Instead of straight invocation to the LLM, I still need to first embed that request, check it against the store, and only then would I go into invoking the LLM. So the takeaway here is that the embedding model and the query of the vector store needs to be super light. I know that sometimes we think it's just going to take us a few milliseconds, but if you take a look at and take a step backward and think of a greater application that also have guardrails in place and other processes down the line, those extra milliseconds might be critical there. So that's really a segue later on when Sherin is going to talk about fine-tuning OpenSearch performance for that use case. Another option, which I'm not going to deep dive, is an open source framework, which was introduced into LangChain framework. It's called GPT Cache. What it does is really, they implemented a lot of interfaces for those different components. So they have an interface for a number of cache stores and vector stores, and they have their own built-in eviction policies. But I don't know if you can see it from here, they don't support OpenSearch. So this is really me taking the opportunity to address this cloud. If anybody wants to step up and contribute code for an open source implementation so that this framework would also support OpenSearch, I think this would be a great opportunity. And the last type of implementation is using the LangChain built-in cache mechanism. This implementation uses the same store as a vector store and a cache store. It does support OpenSearch as both those solutions. As you can see here, the different stores that are highlighted in red do not support semantic similarity cache. This is where, again, OpenSearch shines because you can also use it both as an exact cache and also as a semantic cache. And this is an example of that implementation using, for example, OpenSearch. And by the way, we have, you can download this presentation from the site of the conference where we have links to all different types of source code, so you can have a look there. Again, in this case, where we're asking the same question but with different wording, initially we get a 5-second response versus a 29 milliseconds response with the OpenSearch implementation. This is a sample setup of how do we set up OpenSearch with the LangChain built-in cache. And I just want to highlight here that you also have a parameter for scoring threshold. So this is where you can really fine-tune how similar you want the responses to be. And it ranges between 0 and 1. 1 meaning an exact match caching. One last, or almost last comment about eviction policies. Obviously, when you're implementing your own solution, there is no built-in eviction policies that are handy with LangChain GPT cache. These are some of the common eviction policies that you can think about: least recently used, least frequently used, first in, first out, or random replacement. Just this is a simple retriever of how you can also configure that framework with OpenSearch for a RAG application. In this case, the cache results is also caching the metadata. So both the similarity score, for example, and also the original documents that were retrieved in the RAG application, and then you can use that in any with any of your business logic there. So with that, I'm going to hand it over to Sherin, and we're going to talk about the actual implementation using OpenSearch.
Thanks, Yuri. So we have seen that OpenSearch can be for LLM caching use cases. So we're going to see some quick tips how to start productionizing OpenSearch for this use case. So let's first see some of the OpenSearch memory cache architecture on a very high level. So by default, many of you might have already known that half of the host memory is allocated for JVM heap for OpenSearch when you use start OpenSearch on a host. And it's capped at maximum 32 gig because of some technical reasons. However, it can be increased, but the recommended max size is 32. So that means if you have a 64 gig system, 32 gig, and then rest 32 gig. And if you increase to 128, still 32 gig is the maximum JVM. And within the JVM, we have mainly 3 different caches. One is a request cache. That's where frequently used query results are stored so that when the same query comes again, it could be serviced quickly. And then query cache, similar query data is cached so that similar query comes, it could be quickly given. And the third one is a field data cache, which is used for sort operations, aggregate operations for specific field types like text field. So the default values are enough for most of the use cases. However, you could tune that by checking those parameters shown in the brackets. And then rest of the memory after allocating JVM is left out for operating system like page caching and other use cases. This is very fundamental. But when we enable the KNN plugin or vector search plugin, additional memory will be allocated for storing vectors, right? So that size of more vectors can be put it into. Now, the formula it uses is, as you can see, is the vector memory again will be half of the left out. So if you have a 32 gig machine, 16 gig gone for JVM, remaining 16 gig when we use vector search, 8 gig will be given for the graph memory, and rest will be left over operating system use case. Now, some quick tips. Now, vector search needs memory for in-memory vector search from a performance perspective. There's a parameter called circuit breaker, KNN memory circuit breaker. By default, it's set to 50%. However, if you have systems with large amount of memory, for example, you have a 132 gigabyte system, 32 gone for JVM, rest 100 gig is there. So by default, out of 100 gig, 50 gig will be given for the graph, and then 50 for operating system. Operating system doesn't really need all the time 50 gig. Unless you're not running any other application than OpenSearch in the host, same, because in dedicated clusters, we only run OpenSearch processes. So you can tweak that parameter to give more memory for vector search so that it can load more vector to have more in-memory vector processors. And then, but always mindful of leaving enough memory for operating system and keep monitoring. So if you're using like cloud service like AWS, OpenSearch, there are matrices like KNN, graph memory, and so others. So if it is going beyond certain level like 80%, 90%, that's an indication like you need more memory for vectors. And to optimize that vector memory itself, we have techniques like quantization, vector quantization, which is a technique to compress the vector data itself. So for lower memory environments, you can make use of that. Even for higher memory, you can make use of quantization to further optimize the memory usage so you can fit in more vectors. And if you have really low memory environments, you can use on-disk vector search as well. This is an index level tuning setting. So on this page, the main thing is that you can tune your circuit breaker to allocate more memory for vector search. And in cases of lower memory, you can use on-disk and then enable quantization to optimize the vector resource usage. You can get a lot of more details in those links given below. And now, so we have seen how to tune the memory. Coming to the next step, as a quick tips how to do furthermore optimization when using OpenSearch as a vector engine. One is to selecting the best method, which is the algorithm using how the vectors are arranged in the graph space. So we have two methods supported. One is HNSW and other one is phase. Each of them has its own strengths and weaknesses. HNSW is one of the most recommended because it is, from a search perspective, because LLM caching is a search or intensive workload, HNSW is better, but IVF is pretty good in indexing performance. However, it needs training while indexing, which is an overhead. And then engines are the libraries which implement those algorithms. So we have supported three. The first one, NMSLib, which is under deprecation, so not much recommended for future. Phase and Lucene are the recommended ones. And if you look at the methods like HNSW is supported by all the three. However, IVF is only supported by phase. Now coming to selecting which is the best engine, as you could see, phase again stands out because it supports larger vector sizes. So for larger production workloads with a lot of billions of vectors, phase stands out in combination with HNSW. And Lucene is recommended for smaller workload development environments, smaller workloads, because Lucene uses JVM for vectors. Like phase can use the graph memory, which we mentioned earlier. So that's also, again, a limitation. That's why it is recommended for smaller sizes. And NMSLib, again, is replicated. Coming to the next thing, more knobs to tune. So in HNSW, when we use HNSW method, there are three key parameters which can be tuned for performance versus latency. So for performance versus resource usage. So one is the M, which is the number of edges of each vector, right? And then EF construction and EF search, so other two parameters. Now EF construction comes into the picture when we do indexing, because the indexing performance depends on the value of EF construction, and for search performance depends on the EF search. The higher the value gives more accuracy, more search approximation. However, it will be slower, it needs more memory and more resource. So finding a sweet spot value for these three is a key in getting the performance optimization and the memory usage optimization. Similar to that, IVF have two parameters. One is nlist, nprops. Again, same principle, higher the value, give better recall, but then performance and resource usage will be affected. Now, this is a quick recommendation. So if you want to quickly start with HNSW, which is one of the recommended method, as you could see, if you want optimize less memory and search latency, you can select a value of M for 8 between 8 and 16, and EF construction and search 32. And for balance of everything, latency, memory, and recall, 16 to 32 range for M, and 120 to 256 range for EF construction and search gives good results. And if recall is a key thing, then 32 and 64 M value, that range, and 512 value, which is the highest for EF construction and search. The example there, you could see it's a good start point, like it is a balanced configuration. So in case you want to quickly start, these values are pretty optimized for overall balance to quickly start with, and then you can tune based on your SLA and performance requirements. Now, so we have seen memory tuning using circuit breaker, and then we see the parameters, the hyperparameters for the methods. Now, other best quick quickly doable best practices adopting ML connectors. Now, when it comes to vector search, you have to embed the vectors during indexing and embed the search, search text, the question during search, right? So you could do this embedding on the client side using whatever embedding models, and then send that for indexing and searching. However, if you have very high dimensions, right? So let's say if I say the word high, the word is only 3 letters, but if you make it embed using 1,000 dimensions, that could be a very big 1,000, big vector. So sending that from a client which is pretty remote all the way to OpenSearch cluster deployed or on a data center or on the cloud, it could be slower because the payload can go. So it is always a best practices to leverage the ML connectors and the pipelines available within OpenSearch. And these connectors support a wide variety of different options like hosted models, third-party models, cloud-based models. It offers wide variety of connectivity so that you can offload the embedding process also into OpenSearch rather than do it on the cloud side. And this is easily implementable. You just need to create a pipeline and connectors. And yeah, so we have seen, and then some very quick other tips. Indexing optimization. Now, this is not just vector-specific indexing. This is general indexing, but however, it applies to vector indices as well. So if you're doing a very bulk indexing to start with, it is recommended to finish the indexing quickly. You can turn off the refresh interval, and then once the bulk indexing is finished, you can change it back. That's an index level dynamic parameter. Once it is finished, you can run a refresh manually to perform the refresh, because refresh are resource-intensive operations. So to give more resource for indexing to finish quickly, you can turn it off during indexing. And then disable replicas, which is again a general best practice during bulk indexing. And increase the number of indexing threads. But again, you need to be cautious because it is CPU dependent, because thread means it uses CPU threads. So if you don't have enough CPU, increasing the threads won't give much improvement. It can worsen. So if you have enough CPU resources, you can increase the threads, quickly finish the indexing, and turn it back to the original config. And then again, shard size guidelines applies for vectors also. For really small ones, small indices, one primary, one replica is enough for most of the use cases. And for larger ones, since it's LLM caching is a search-intensive use case, 25, 30 max size per shard is the recommended max size. And then again, that's the last one there is keeping larger segment size with fewer segments. That gives better performance when it comes to vector search. And it can be implemented by performing force merge periodically during off-peak hours to merge smaller segments into larger segment, and also by increasing the flush threshold size. You could see some examples on the right side how we could quickly do this. And coming to search, again, from the previous slide, same thing. Reduce segment count, one or fewer segment per shard provides optimal search latency. And for vector fields, you could warm up the indexes by running few queries, or there's a warm-up API which can be executed after you're loading a lot of vectors data, run this warm-up API, so it will put those vectors into memory, so that will be the queries when production queries comes in, it will be faster because it can take it from memory. And then avoid reading stored and vector fields, like underscore source fields may have a lot of data. Only when you do queries, only specify whichever is needed, and you can turn off the source reading everything by putting that into false, as you see in the example. Also, the vector field itself. Let's say you're doing a vector search, you're giving the vector as an input. You don't necessarily need that vectors back in the response. So you can avoid that as well. Only the necessary field comes back as a best practice to improve the search performance. And in OpenSearch 3.x, there is a feature which automatically do this, avoiding the source field thing. And then second last is enable concurrent segment search. So from OpenSearch 2.13, there is this feature called concurrent segment search. which can parallelly read multiple segments in a shard. So traditionally, in a shard, when a search happens, segments were read sequentially one by one. So if you have more than one segment and you have enough CPUs, you can parallelize that read to improve the search performance. And this can be done by tweaking an index level setting, as shown in the example. So you can turn it on. I heard from 3.x onwards, this is enabled by default. But if you're on production with 2.13, 17, 19, it is a good idea to turn it on. And this is applicable not just for vectors. In general, any searches can make use of concurrent segment search. And there is something called slice counting, because a slice count defines a parallelism by default. When you enable this feature, 2 will be the number of slices. You can increase the slice count also dynamically if you have more CPUs to read more segments in parallel. And then finally, vector search is again a memory heavy stuff. So use higher instance type for real production use case to have enough memory, and then tweak the settings, which we already discussed. And some cost optimization quick tips. So these are some quick tips, which is quickly doable. Use quantization to optimize memory so that less memory can be used, so you can have smaller instances. And use a very relevant size model for embeddings, and select the relevant dimension as well, so that it will reduce the overall memory and usage and the resource usage needed. And then replicas. Now, see here is an example with a formula and a substitution for a 1 million vectors with 384 dimension. You could see that 1.83 gig will be the size for each vectors. So if you have so much of vectors, the memory size will be more. And if you have more replicas, each replica nodes also need the same amount of memory. So be mindful of using the model and the dimension. And wherever possible, for lower environments like development testing, and for infrequently accessed indices, use disk-based vectors rather than using in-memory. And then when you are using cloud-based deployments, explore various options like serverless, tired storage, reserved capacity, and all. And always benchmark your workloads using different hyperparameters, different instance type, different circuit breaker settings, different method options to finalize the best configuration, rather than just starting with bigger configuration and adding more cost. There is a benchmarking tool available which can be downloaded and used, which has vector workloads also as an example for if you want to try some benchmarking and testing. And there is a published benchmark results available as well if you want to quickly start with some values because not enough time to do the testing. Links of that is given below. And finally, to conclude, tuning optimization is not a one-time. It evolves when you have changes in workload happen. So as high level, just to conclude what we said, so tune vector memory settings, as you see in the very first slide, and tune the index level settings like the hyperparameters method, choosing the method and engines. Use OpenSearch pipelines and other best practices, and implement shard and indexing level, indexing and search optimization, adopt cost optimization, and always do benchmarking to finalize your configuration. Yeah, that's it. Thank you. Hope it was useful. Yeah, a few minutes.
Any questions?
A few minutes, yeah.
For me or for Sherin? Sorry. I'm sorry?
Please call it the LLM cache rate. What was this like in production?
What was?
The LLM cache rate.
The cache rate? It depends on the application.
So in this
First of all, the greater the cache is, obviously the better chances of having a cache hit there. It also depends, again, semantic versus exact cache. I can tell you that for the healthcare customer that I mentioned in the beginning, we were able to decrease LLM invocation by 50%, and we did it, it was really conservative. Like we really weren't being aggressive on the embeddings or the similarity there. So we were able to reduce their LLM invocation by 50%.
And on that, you also measure the satisfaction or the quality from the end user to say if they are satisfied.
So, okay, so first of all, I don't have 100% visibility into the customer satisfaction because we as AWS provide the infrastructure and guidance for customers who are actually monitoring their end users' satisfaction. But again, since latency issues were reduced for at least 50% of the invocation, I assume that customers were happy with that, and it ended up in production. No problem. Yes, please.
It's open. It's in OpenSearch. Yeah.
Yeah.
Yeah. So if you use a face engine, enable the KNN, that's allocated as a part of the KNN plugin. It will be there. Graph. It's called KNN Graph Memory. Yeah. It's not AWS. It's in OpenSearch thing. Yeah.
Thank you very much.
It's all.